Test. Are we on? Can anybody hear me? Let's do this. So it looks like we have 30 people. Can you hear me? Emre says yes, yes, we are on, yes. So you say yes because you hear me, right? Okay, good. So we have 28 people, 27 people. That's our usual number. Okay, is my sound clear? I mean, I couldn't connect this thing. It looks like it is doing something, but okay, then if the sound is okay, let's start. So last time we talked, it was let me try to make my pen work. It looks like I am out of my batteries ran out. Let me grab a battery. Okay. I hope this works. No, for some reason it didn't work. Did I? No. Let me try to put this back in and out. Okay, it works now. So the last time where we stopped, we were talking about interprocess communication. We said that we like to we like our isolation, our abstraction between the processes or threads, but we like to communicate between the threads. So what would be the problems if we try to do this? So first we say that how we can pass information to another process or thread. For the thread, this is no problem. I mean, for the threads, this is no problem because threads, they share lots of stuff, including the address space, and our global variables will be shared. The second one is if two processes are working or if two threads are working on the same data, same memory location, how can we make sure that one is not get in other's way? So let's not do this. And the third one is dependencies, sequences and dependencies. If A is producing something and B is printing it, this is a process, this is a spooler, and B should wait until the data is ready. So mostly we will be looking at these two. Okay. So this is what we were doing. Okay, we have lots of people. We have 59 people now. I think I have lots of delay. Okay. So to start with today, can I have a question? Okay. Just ask me a question. Somebody ask a question. People are saying yes. Also, there is some of them are so late. I think some of them are playing the recorded thing. Questions so far? Okay, I will continue, and when I get the question, I will try to answer it. Okay, so there is this thing called race conditions, and we don't like the race conditions. We will try to eliminate them. The definition of race condition is this. Definition of race condition is this. You have more than one process running or thread running. When I say process, you understand it as process or thread. It doesn't matter. If they are reading or writing some shared data, the final result should not depend on who runs precisely when. Okay, if the final result depends on who runs first and who runs second, that's the race condition, and we don't like it. That's the classical example is the printer spooler. Let's say your processes, process A and process B, they are trying to print out some files. What they need to do is they write their file names into this buffer, okay? And the spooler takes the file name from this buffer and prints it out. That's what it does. So the race condition means that if process A writes, let's say process A likes to print file A dot, let's say CPP, and this is what process A wants. Process B wants to print file B dot, let's say TXT. Okay, what they want is process A and process B, they want their files to be printed. They don't care which one is printed first or last. It doesn't matter. So as long as my output is always printing two files from these two processes, I am okay. But due to some problems, if file A is not printed or file B is not printed or file A is printed two times, that's a problem. That's a race condition. So we don't like race conditions. I don't want my output, my final results, to depend on who runs precisely when, who runs first, who runs seconds. Okay, so obviously the user doesn't make any selections about who runs first and second. The user says that I like these files to be printed, and that's what the output should be. Okay, so that's the race condition, and that's the case that we like to prevent. Okay, we have a question. That's the very first question that I have. Why is the first one not a problem for threads? Okay, the first one is not a problem for threads. Anybody has an answer for that? Why the first one is not a problem? I think I already said that. That's because with the threads, you have the shared address spaces. All the global variables are shared. So if I modify one global variable, all the other threads are going to see it immediately. So how one process can pass information to another is not a problem for threads. That's what you get. Okay. What about local variables? Well, I mean, you don't want to share your local variables. Local variables are local variables. That's why you have your stack, right? You don't want to share your local variables. Sharing local variables is not a good idea because remember, the local variables are used for your stack. You use your stack to keep your local variables, and in your stack you have your return address, you have your function call parameters, and etc. You don't want to share them. That's why you have your stack. Otherwise, with the threads, you would have shared your stacks too. Okay. Just a minute, I am coming back. Let me grab some coffee and I will be back. Sorry, I am back. Okay, so as we said, local variables, we don't want to share them because they are our private data. Globals, we share them. That's the idea. Using the globals, we can communicate with the other threads. For the processes, no globals or no locals are shared anyway. So we need to deal with these problems. The problem is if you start sharing the data without any regulations, you start to having these race conditions. And last time we talked about the race conditions. Okay, let me check my stream again. My analytics are my stream health is. Where is my stream health? Yeah, here it is. Excellent. Okay, good. Okay, good. So for the race conditions, I think we gave this example. Two processes, or let's say two threads, trying to. Okay, let's look at this picture then. Two processes are trying to write to the position so that their files will be printed out. I think it would look like this. Process A is trying to write file A into this position N. Okay, N is 7. And process B is trying to do file B at the position N. Okay, it looks like it's just fine. And if the process A runs first, it will say that, okay, these are our globals, in and out and string buffer. Okay, so I have at most 100 elements. I could have at most 100 elements in this one. Okay, so currently my value in is 7. Let's say file A is inside this. Okay, process A is running. File A will be printed at this position. File A and in will be incremented by 1, and then process B will start. Process B will start and it will say file B will be here because it is 7 now. It will make it 9. So at the end, my in will be 9, and my A will be my in will be 9, and I should be okay. It should work this way. What happens if process B runs first? Then in this case, the output will be, this will be B and this will be A, no problem, right? Well, you would say that, well, output has changed. Is there a race condition here? Well, I mean, we don't have a race condition because of this. Output did not change. The output is the spooler will get these two files and they will be printed eventually. All process A wants its file to be printed to the printer, and process B wants its file to be printed at the printer. No problems. So doesn't matter if A is printed first or B is printed first, as long as they are both printed at the end of the day. Okay, but the problem is this. Let's say I am the CPU and I'm at the beginning. I am at the beginning. Okay, I am at the beginning. I am the CPU. I am at this my PC. Again, the pen problem. Let me solve the pen problem. The PC is at the beginning of the file, process A or thread A. Okay, PC is here. It said that, okay, I will put my file A into this position N. So it write file A here. File A, no problem. Okay, no problem. And then PC is here. Program counter is now here. Then after that position, operating system decided that there is an interrupt. Operating system decided that process B should start running. Process B will start running. And process B will come in and it will say that, okay, I will put at this position file B. The value of N is 7 because A didn't get to change it, didn't have the opportunity to change it, modify it. So instead of file A, it will erase file A and it will put file B, right? Okay, and it will increment in by 1. Okay, it will execute this one, execute this one, execute this one, and execute this one. Okay, then I got another interrupt, and the operating system said that let's go switch to process A again. I am at the process A, and process A says that I will increment A by 1. Okay, I will increment A by 1, but it says that, remember, it took, process A took the in as a register in its registers, and registers are local. So in is still 7 for process A. It will increment it by 1, and it will be now again 8. 7 plus 1 is 8. So it will put 8 in there too. Okay, it will put 8 in there, or it doesn't matter. I mean, it would put 8 in there depending on your optimizations, or sometimes it will put, instead of 8, it is 9. Okay, so at the end, what I see is my in will be pointing to this position. File A is now erased. I don't write it. Okay, file B is written in there, and the 8 position, depending on your implementation, is empty. So it is all messed up. This is what we call race conditions. Okay, this is what we call race conditions. Okay, and we don't like these kind of race conditions. We say that this should not happen, because depending on what was the definition, depending on who runs first, when the interrupt happens precisely, our output, final output, should not change. So we should prepare it. We should have a way of preventing this from happening. That's why we call that, we need is mutual exclusion. We say that if I am as process A or thread A, if I am doing this pen is going wild. If I am executing this piece of code, this is my critical region. And again, this is my critical region, both of them. If I am inside my critical region, I am mutually exclusive. If I am inside this region, nobody should be able to enter their critical region. So if I am process A, if I executed this one, remember what happened last time? If interrupt happens here, then that's a bad thing. I am saying that even if the interrupt happens, this process B should not be able to enter its critical region. Okay? Only one process can be inside the critical region. Either I am executing this, or I am not executing anything at all. Anything inside the critical region at all. Okay? So I should be mutually exclusive with these two processes regarding the critical regions. That's what we need. Okay? Okay, so last time we talked about this, and I think I gave this example, and I said that let's implement the critical region like this. Let's make a global variable. Let's say integer lock, and its value is 0. And let's do this. If lock is 0, then I would enter this critical region. As soon as I enter the critical region, I make lock 1. And when I leave the critical region, I make lock 0. And I do exactly the same thing here. If lock is 0, then I make lock 1. And before I leave the critical region, I make lock 0. Okay, so this kind of achieved what I wanted to do. Why? Because If process A is inside this region, since it made lock immediately 1 right after it entered this region, process B cannot enter it. Even if I have a interrupt while I am executing this. Let's say there is an interrupt happened here. Let's say there is an interrupt happened here, and process B started running. Okay, process B started running. The process B cannot go into this region. Why? Because lock is 1 now. Lock is not 0. Okay, lock is not 0. Usually, let's not do it this way. Usually people do it this way. They say that, okay, they say this, okay, while there is a while loop, while lock is not 0, then wait. Okay, so there is an infinite loop there. Let me try to get this one and duplicate it and put it in there too. Okay, so this is what I do. If lock is not 0, then I will be in an infinite loop in there. If lock is not 0, then I will be in an infinite loop in there. So none of them will enter the critical region. So what was the problem with this approach? Last time we saw this, right? What was the problem with this approach? What if yes, Barish says what if interrupt comes in right after the check? He means let's say lock is 0. Okay, since lock is 0, I don't enter this loop. I come here, but what happens if the interrupt comes at this position before I get to change the value of lock, right? So if the interrupt happens there, again, I have a race condition. You may say that the chances of having this happening is like maybe 1 in a million, 1 in a billion, doesn't matter. The computer world is so fast, okay? CPU runs so fast. So since it is running so fast, there is a good chance that something will happen, okay? So Emre, what do you mean by busy waiting? I think, yeah, this is what I'm doing is busy waiting. This is called busy waiting. Emre is asking a question. Busy waiting is, I am waiting something to happen, but since I am waiting, I should not do anything, but I am busy waiting, okay, right? So I am running a loop, so I am keeping the CPU busy. While I am running the loop, an interrupt will happen. This process will start, and it will go on, and it will eventually make the lock available. Of course, if one of the processes or threads, they don't update the lock as 0 right after they leave the critical region, that will put me in an infinite loop. So since, what did we say, remember? If we are writing multi-threaded programs, they are supposed to help each other, okay? If one of them is not behaving correctly, then that will take down the whole program. Okay, so the critical region idea is nice, but implementing it this way is not a good solution. The book had a example program that prevented this using the strict alternation approach, and we will say it. And without skipping these definitions, mutual exclusion, some way of making sure that if one process is using a shared variable or file, the other process will be excluded. This is my critical region, and this is my critical region. I am mutually exclusive here, and I am mutually exclusive here, but I could not be successful because if the interrupt happens at that position or at that position, it's going to be bad, right? It's going to be bad. So a part of the program where the shared memory is accessed is called the critical region or critical section. This is my critical region, and this is my critical region. So critical regions, if you satisfy all these conditions, then you have a healthy critical region. No two processes may be simultaneously inside their critical regions. The solution that I showed you is not a good way of achieving critical region because it did not provide it, right? No assumptions may be made about the speeds or the number of CPUs. You cannot say that my CPU is not that fast. There is a very small chance of having this happen. No, you cannot assume that. And the number 3 is, if you are outside of your critical region, if everybody is outside of their critical regions, there should not be no reason why you should not enter, why you cannot enter your critical region. Okay, the only reason you cannot enter this critical region is that lock is not 0. Okay, if the lock is not 0, that means that somebody is in their critical region. If everybody is outside of their critical region, you should be able to go into the critical region. That's the third thing. And the fourth thing is that no process should have to wait forever to enter the critical region. Okay, so that's the fourth criteria. If you satisfy all of these, then you have a healthy critical regions. Okay, we talked about this. Okay, so what are the ways of achieving critical regions, mutual exclusions? Okay, we will keep using this technique, busy waiting, an infinite loop. Okay, an infinite loop that tries to see if a variable is changing or not. I mean, for a regular C programmer, this doesn't make any sense, right? This line doesn't make any sense. Why? Because nobody's changing lock, okay? And this is definitely an infinite loop. This program will never end, you would think. But even in a multi-threaded program, since lock is a global variable, this thread or this thread can change it. While I am running this loop in this thread, the other thread is working and doing its thing. And as you see, it changes lock to 1 and it changes locks to 0, back to 0, etc. Okay, so I write this program myself, and I should be careful about, since I am trying to write a critical region, I should be careful about those 4 criteria. If I don't update this lock at the end of the critical region, then there is no way this process can enter the critical region. So it will wait there infinitely, and I will violate the rule number 4. Okay, good. So that busy waiting thing here is used a lot. Doesn't make much sense for a regular C programmer, but if you are a multi-threaded, if you are writing a multi-threaded program, then this makes sense, because I am having this too and having this too. Okay, so this is called busy waiting, and busy waiting is very simple solution, very simple technique to deal with the critical regions, and we will see it. Okay, so there are other ways of doing the mutual exclusion of critical regions. One is disabling interrupt, we talked about it, lock variables, and we talked about it, string alternation, Peterson solutions, and TSL instructions. Okay, Ali Emre Büyükersoy, does it matter if we use 4 instead with ++ lock? Yeah, I have a good answer for that one, and we will see in a few minutes, Ali Emre. Okay, that's a good question, and I think we talked about it. Oh, okay, we started with 80 people, now we have 69. Okay, good. My stream is healthy. Let me check my analytics. Good. There are many playbacks. Chat rate, what is chat rate? Oh, okay, so at the beginning I have a peak. Playback. Some people are coming from behind, I guess. They are playing it. Okay. Let me keep it at the health thing. Okay, so these are the ways of achieving mutual exclusion, and some of them may involve the busy waiting. And we said that disabling interrupts last time, remember, we said that disabling interrupts is not a good idea because as a regular thread, it is not available to me. Okay, I don't have the privilege to change the interrupts, disable or enable it. Okay, because that would be a too powerful thing for a user to have that permission. And for the multiprocessors, you disable the interrupts for a processor. How about the other processors? And well, sometimes we use really disabling the interrupt technique, a special case, but it is done with the kernel. So let's keep this idea in our pockets, and we will come to this later. But for now, this is not a good solution. The second one is again lock variables. That's what I did. That's good. I mean, if the lock variable is not 0, then make lock and enter the critical region and end of the critical region. It does not work because, as we said before, it's not if the interrupt happens at the worst moment, then I will have a race condition. Okay, this is the answer to Ali Emre's question. What happens if I do this? If lock is not 0, it's like this, right? If lock is not 0, then decrement lock and go into a loop. Okay, if lock is 0, then I will increment it and I will go to my critical region. But this is you understand this code, right? So it looks like it checks the value of lock and it increments it at the same time. So you might think that there is no way an interrupt can happen. But if we look at the machine code, okay, assembly code, first load lock from the memory position to register 0. And then I move from register 0 to register 1. And I increment R1 by 1. And I store R1 back to the lock. And I compare R0 with 0. Okay. And I do this. Then I enter the critical region. It looks like I need 1, 2, 3, 4, 5 assembly instructions to achieve this part of the code. So if interrupt happens here or there or there, I am in trouble. Okay. So lock plus plus is not atomic. That doesn't solve your problem. Okay. So the book gave an example. It said that I have this idea. It will say that there is a global variable named turn. Global variable named turn. It is integer. At the beginning, turn is 0. If turn is 0, this thread can enter the critical region. If turn is 1, this process can enter the critical region. It says that if the turn is not 0, then I will be in an infinite loop. Busy waiting. If turn is 0, I will enter it. Oh, electricity. Okay, good. If turn is 0, then I will enter the critical region. As soon as I am done with the critical region, I make turn 1 and I do my non-critical region part. And I will go to top of the while loop. Okay. And since I made turn 1, this one can enter the critical region and turn is 0 and go back to the top of the loop. Okay. Okay. So I am doing this busy waiting here. And this kind of lock is called a spin lock. Okay. A busy waiting, but I am doing this in a loop. Okay. This is called spin lock. Spin lock is just one way of achieving this busy waiting technique. Okay. So this works. I mean, it doesn't matter because see what happened before. When I check this turn, okay, if it is 0, then I enter the critical region. Doesn't matter if the interrupt happens here or inside the critical region or there, because I did not change my turn to 1 yet. Without changing turn to 1, this will not go into the critical region. Okay, since I modify my turn at the end of the critical region, okay, there is no problem, and the same thing is here too. So it kind of solves the problem, but if you remember last time, what we said was, let's say this loop is so slow, okay, this loop is so slow. Let's say this one did the critical region, made it turn 1, it is in the non-critical region, okay, this one runs critical region, okay, let's say this critical region happens and it makes turn 0, and it is in the non-critical region. It is inside the non-critical region, but let's say this non-critical region will take maybe 1,000 seconds to handle. But it's okay, because since turn is 0, this will go top of the loop. Turn is 0, critical region, turn is 1, non-critical region. Since this one is in the non-critical region, but it is taking so long, this one will come back to the top of the loop. Since turn is not 0, okay, because it made the turn 1, this has to wait at the top of the loop. So this one is waiting at the top of the loop, but this one is not in the critical region. So that's a problem. That's a violation of rule number 3. The rule number 3 said that if the critical region is available, you should enter it. This one is outside of the critical region. It is preventing this one from entering the critical region. That's why this is called strict alternation. Okay, strict alternation. Strict alternation is not a good solution for mutual exclusion or critical region implementation. Okay, the situation violates the condition number 3 set out above. Okay, so this was kind of review of what we did last time, and let's say we said that we will find a solution for this. It's going to be a very small and smart solution, and we will see it in a few minutes. Any questions so far? The advantage of having an online course is, if you like to ask a question, you can use a Google Translator or something. Or just copy the question from the book at the end of the chapter. There are questions, right? Exercises, and ask them to me. Okay, no. I guess no questions. Okay, I will continue then. Good. So this is the solution that doesn't use a strict alternation. It is very simple solution. Okay. All you do is you say that I have two functions, enter region and leave region. Okay. When you enter the region, you call this enter region function. When you leave the region, you call this leave region function. If we go back to the original program that I showed you, where is my original program? Yeah, here it is. Let me erase all of these, since I'm going to use it. I will say that, okay, this will be enter region process number 0 and leave region process number 0, and do exactly the same thing with the other thread, but this time don't say 0, but I am process number 1. That's what we do. Okay, before entering the region, I call this function, and right after I leave the region, I call this function leave region. Okay, but you say that I am process number 0 and by process number 1. Okay, so let's go back to the Patterson solution. Patterson solution, I think it was proposed in 1980s. People had solutions for this problem before, but their solutions were much more complicated, but this is a much easier solution. The idea is kind of double lock, okay? When you try to enter your critical region, you say that I am going to enter my critical region. You are warning everybody else. And after that, you are trying to get the lock. If you can get the lock after the warning, then you are gonna enter the region. If you warn everybody and everybody else says that okay, it's okay, then you're gonna enter it. If somebody else says that I am interested in 2, then you have to wait, etc. So this is the basic structure. Again, we have global variables turn. Turn is either 0 or 1. Okay, since we have 2 processes. This is generalizable to n processes, doesn't matter. Okay, for now I have 2. And I have an array of integers interested. So let's do this then. Let's say in my memory global, there is a turn and there is this interested array at the beginning. It's like this. So turn is 0 at the beginning. And interested is actually this is a Boolean. Let's make this Boolean, okay? This is okay. Read this as Boolean, okay? Since 0 is false is 0, true is 1. Okay, I'm going to make this again interested. Interested. At the beginning, it is both false. If I put a true in this slot, that means that I am interested in entering the region. And if I put an F, that means that I am not interested. So if some process calls this enter region, let's say I call this enter region with the process number 0, int other is 1 minus process. If it is 0, then other becomes 1, right? And I say that I am process number 0 and I am interested in getting into the critical region. So I will make this okay, pen again. I need to buy one of these. Just they are so expensive, 600 liras. You can buy a laptop computer for 600 Turkish liras. Okay. So let's make this true. I am interested. And I will make the turn 0. Okay, it is 0. So I am into this loop now. See, there is a possibility of busy wait. Okay, so it says that if the turn is the process, I made it just a process. If the interested other is true, that means that if the other one is interested, what is other? Other is 1, right? If the other process is interested and the turn is my process number, then I will wait because the other one is trying to enter the critical region too. If the other is not interested and if the turn is process, then I will not enter this loop and I will exit from this function. Since you exit from this function, that means that what? That means that you can go to your critical region, right? So if the other one is not interested, since turn is process, I am not going to wait in this loop. Let's say the other one is interested. What does it mean if the other is interested? Other is interested means that the other process has run. It made its interested field true. It made the process turn its number. Turn is 1. Okay. Now that means that the other process it did both of those and it get out of this loop and it entered the critical region. Okay, so I cannot enter the critical region. I need to wait from at this point here. Okay, and when I am leaving the critical region, I just make this false so that the other one can enter. The other one, let me make this one even better. Okay, so let's try to make this break. Let's try to see if interrupt happens at the right position. If the interrupt happens at the right position, there is a race condition. Let's try to say this. Before that, let's see if the number 3 can happen here. What was the number 3? Number 3 said that if somebody is outside of their critical region is making other processes wait, then the violation of number 3. Obviously, this will not happen because every time I enter my critical region, I am interested. This is my turn. I am not into this loop. And when I leave it, I make it false. Okay, so I am not talking to the other process at all. So I can enter my critical region and leave it as many as I like. No problem. Okay, so number 3 is not a problem. Let's see if number 1 becomes a problem. That is, 2 processes could be in the critical region. Let's say when I am entering the critical region, let's say interrupt happened here. No problem, I did not change anything. Interrupt happened here. I said that I am interested. But I didn't change turn to process. In that case, the other process will start running, and it will make its position again true. So both of them will be true. This one true and this one true. Okay. So since both of these true, both of them are interested, only one of them will see a turn equal to process, and that one will wait. The other one will break this loop and will go into the critical region. Okay. We always talk about 2 processes that have the critical region. How about these solutions work for the 2 processes? Well, I think Furkan, I talked about it. This is easily generalizable to more than one process. Well, in that case, what are you going to do? More than 2 processes, sorry. N will be, let's say, 100. N will be, let's say, 100. And when you do that, you need to check all the other interested parties. If this condition holds, then you need to wait. Okay? Then you need to wait. So this is generalizable. And I think, in fact, there is a good question at the end of the chapter to make it generalize to more than 2 processes. This Patterson solution is generalizable to more than 2 processes. Okay, so remember the interrupt happened here right after I made this one. I made this modification. The important things are actually the modifications. Right after the modification, what happens if the interrupt happens? Okay, since you are not changing the interested field of the other process, you are only reading it. There is no problem regarding the interested. Okay, so you might say that why do we need this turn now? Turn is for double locking. Okay, you say that I am interested. You are broadcasting to everybody, and you are trying to lock it, and you are checking it. Anybody else is interested? No. Is it my turn? Yes, then I could go into the loop. If somebody else is interested, even if it is my turn, then I will wait. Okay, so there's a smart solution, smart and easy, smart and simple solution to achieving mutual exclusion with busy waiting. Busy waiting is happening here, see? Busy waiting is happening here. And of course, when I leave the region, there is no busy waiting. Good? Any questions so far? This is not good. I need people in front of me. It looks like I am talking to myself. Maybe I should call the TA and TA should stay here. I don't know. I mean, watch something on. Okay. So let's continue. This is Peterson solutions again. Busy waiting. It's done. Why did we do this? Because this one didn't work. We did this because this one didn't work. If we had just an instruction that just increments a variable and checks its value at the same time without any possibility of interrupts, that would have solved all the problems. Okay, that would have solved all the problems. We couldn't do this. That's why we had to invent this double locking mechanism. Is everybody else, is there anybody else interested in this region? I am interested. Anybody else? Is it my turn? Can I enter it? So 2 questions at the same time. I need these 2. But if I had an instruction like this one, TSL, a special instruction, it is supported by the CPUs, TSL, then I didn't need the Peterson's algorithm at all. TSL does this, okay? TSL does this. It reads the contents of the memory from this word lock, from the memory, okay? It reads them to this register, Rx, and then it stores a non-zero value at the memory address lock, okay? So if I say, let's say, TSL R0 lock, okay, and this is my memory, this is my register 0, this value is 0, and this is my memory position lock, this value is 0. If I execute this, then it does this. It takes this value from this lock position to the register, and then it puts a 1 in there. So a register 0 was 0 at the beginning. It didn't make much difference. But let's say this. If the situation is like this, okay, if the situation is like this, if I execute this one, it will transfer this value, it will copy this value to register 0, and it will put a 1 in that position. Okay, it is doing 2 things at the same time. It is copying the content of this lock variable to R0, and it makes this lock a non-zero value. It is done at the same time, and there are CPUs supporting this operation. So there is no way, while I am doing this, there is no way an interrupt can happen. Okay, the CPU guarantees it. The operations of reading the word, okay, and storing into it are guaranteed to be indivisible. There is no questions on it, okay? If the interrupt happens while I am doing this, then that's the problem of the CPU. There is a bug with the CPU. Okay, so how do they implement it? They lock the memory bus. Okay, they don't, while they are executing this instruction, they don't disable the interrupts. They lock the memory bus. That means that nobody can have access to the memory. Well, that's a dangerous thing. Maybe it is inefficient, but it is, I mean, it is just a very, very small amount of time. A very, very small amount of time. Nanoseconds we are talking about. Okay, so that's a very short amount of time, and you don't use this instruction very often. You only use this instruction at the beginning of your critical region. Okay, good. So let's use this in a busy wait structure. Okay, Mustafa has a question. Are the atomic variables infrastructure like that? Oh, Mustafa, I did not understand your question, Mustafa. What do you mean they are infrastructure, atomic variables? What's an atomic variable? It's an atomic instruction, I said. Did I say something wrong? Sorry. By the way, if you like to ask questions without typing, you can call me. Here's my office number. Let me type my office number. Yeah. Here's my office number. 262 If you like to ask a question, then just call me. Maybe that would be more direct way of. That's called Turkish teleconferencing, Turkish online teaching. Okay, so Mustafa, either just call me or tell me what you mean by infrastructure like that. Okay, do you think we should switch to Teams? Is anybody using Teams? Google, Microsoft Teams? Is it better? Should we switch to Teams? Teams, I think with the Teams you can talk to the instructor, but I'm sure there is a delay too. Oh, my phone number is wrong. Sorry. This is not. Let me change it. Remove it. And it is this 2221. Like this. Yeah. I hope you didn't call somebody else. So you call somebody else and you ask a operating system question in English, right? And that somebody has to be in Gebze too. Yeah, that should be funny. Okay. It's Microsoft Teams, so I don't. What do you mean? It's an online thing, Yusuf. You don't have to install anything. You are using Microsoft Word, right? Anyway, okay. So Mustafa is thinking about his question, and I will continue. By the way, maybe I should take a break because it has been an hour. YouTube is good enough. Maybe I should take a. Maybe on Teams, and we could give more accurate answer after Teams. Better for conferencing, broadcasting lectures will be better in YouTube. Okay, let's continue with YouTube for a while. But if we find some advantages of Teams, because with the Teams I think I can take the attendance and we can control, because this is public, everybody can enter it. I don't know who's listening. I don't know who's listening. Maybe we should control who is entering these broadcasts. So we will continue with the YouTube for a while, and later if we have problems, issues, we will switch. Okay, let's take 10 minutes of break. After the break, we will continue. Yeah, Mustafa he wrote his question. When I say infrastructure assembly code in TSL, yes, the CPU directly supports the TSL instruction, test and set lock. And you don't introduce to your CPU. It is not an operating system feature. It's a feature of the CPU, TSL. Okay, it is designed for multi-threading and inter-process communication. Okay, 10 minutes of break. I think I am watching it in 1080p, not 70. Okay, 1080p I am broadcasting. It depends on your download speed. Is anybody having any problems with the YouTube making it slow? Because I think everybody is doing their courses online today, and I thought that it would put some stress on the Turkish internet structure, but it looks like everybody is watching the YouTube videos anyway all the time, so we are not putting any extra online stress. Okay, so It is 11:30 now. Let's come back together at 11:40. 11:40. 11 11:40. I don't know exam date. We will have to wait for that one. For the exams, we don't have any. We don't have any question. We don't have any solutions yet, because I don't know how to make an remote exam. That would be unfair for some people. I don't know. Even this solution, broadcasting our classes to you on the internet, is not a very fair solution, because not everybody has fast internet connections. Well, I am. Oh, I forgot something. You know what I forgot? I forgot to record my lecture. Well, it is saved by the YouTube, but okay, now it is recording. So sometimes there is a gap while I'm talking with the YouTube streaming. So next time maybe I should not forget. So it is both streaming and recording. Okay. So let's see in a few. I'll see in a few minutes. Some universities cancel their whole term for teaching. Really? They can't do that because they need a permission from Higher Education Council. Those universities are American universities as far as I know. Gökçe, what university did this? Anyway. Okay, this coffee is too cold. I need to get some coffee.
Kolay yaptın.
Baksana yine beyaz beyaz duruyor. Yok kızdan kızmaya ondan takip ettim.
Aa, burayı yıkamışlar ya. Bu ne ya? Evet. Hani Gökçe, göremiyorum öyle bir şey burada ben ya.
Bana bir şey olmaz.
health. Okay, let's start. Is everybody ready? Type yes. My health is poor. What's going on? YouTube is not receiving enough data. Okay, we will read it later. Okay, yes, good. So, stream settings, analytics, chat rate. What is the viewers? Okay, good. Okay, so TSL is a special instruction supported by the CPU, and it does this. It reads the contents of the memory word into a register and then stores a non-zero value to it. So this is what you do. Instead of calling this enter region with the process number, okay, you only just call this simple function enter region. Remember, note that you don't send your process ID. You just say that I like to enter the region. It says that, okay, load, copy the contents of lock to this register and put a non-zero to lock, and compare the value of lock against 0. Okay, if not equal, go to enter region. So busy wait happens here. Okay, if not equal, that means that if the loaded value from the lock is not 0, then that means that somebody has the lock. It should be 0. I like it to be 0. Okay, if it is not 0, then I will wait. I will do this again and do this again and do this again until I get the lock value of 0. Okay, since if the lock is not 0, if it is 1, my register value will be 1, right? And I will compare 1 with 0, so it is not there. And again, when I go back to top of the loop, I will do the same thing. And since lock is not 0 at the beginning, doesn't matter if I store a lock value of non-zero value to there. And at the end of the critical region, I just move 0 to lock. Okay, so if you have the TSL instruction, you don't need the Peterson's algorithm. You don't need a double lock mechanism. It all works. Good. So again, that's a many times we will say this. If we cannot solve a problem efficiently with our operating system, we will ask help from the CPU, from the hardware. Okay, so we will ask the hardware to do something for us. If it is possible, the new CPUs will support it. If it is not, then I have to do it the tough way. Okay, so at the beginning the CPUs didn't have this TSL. Now they have it. At the beginning the CPUs didn't have the virtualization support. Now they have it. At the beginning the CPUs didn't have support for the hyper threading, more than one thread happening at the same time. Now they have it. Okay, so most of the time the changes for the hardware comes from the operating system designers. Okay, another instruction alternative to TSL. I think the TSL is patented. Not everybody can use it. Intel uses exchange instruction. Exchange is supported by Intel CPUs. Exchange supported by the Intel CPUs. Exchange does this. When you say exchange register with a lock, it does exactly this. It copies the contents of the lock to R0, R0 to lock. Okay, and it is done at the same time, indivisibly. Okay, it cannot be divided into two. And if I like to implement the same thing with exchange, this is what I do. I move 1 to register, then I exchange the register value with the lock, and I compare the register value with 0. If I get a 0 from the lock, that means that I can go to my region, critical region. Otherwise, I need to go to the top of the loop, jump not equal. Okay, so very similar. Idea-wise, it's very similar. Okay, good. Any questions so far? So the spin locks, like this one, or this one, or this one. The spin lock is here, right? Here's our spin lock. Are the techniques that we have used so far to handle the develop solutions for this critical region idea. Okay, that was a spin locks. Okay, test and set lock, Patterson's algorithm, or any other type of solution. Spin lock. Okay, spin locks are good, but I mean, for really very long periods of time, it's not a good idea because you are wasting your CPU time. You test it, you go to the beginning, you test it, you go to the beginning. I mean, if I do this only a few times, that's okay. Only a few times, that's okay. But if you are doing this millions of times, that's waste of CPU time. That means that the other processes are spending so much time in their critical regions, depending on your application. It is okay. I mean, you may have to wait, but while you are waiting, you are wasting your CPU time. That's not a good thing. Because if you didn't waste your CPU time, maybe the other process will quit from the critical region in a short amount of time. So let's look at this problem. Acceptable for short waits, especially on multiprocessors, but for longer ones, we need a solution that says, I'm going to sleep. If this happens, you'll tell the operating system that I'm going to sleep until this lock is ready. Okay, let's try to design something for our operating system to eliminate the spin locks, or at least to reduce the effects of the inefficiencies of the spin locks. Okay, that's one thing. Okay, we need to be careful about actually spin locks a lot. One for efficiency, the other one is there is a very serious problem for this one. It's called priority inversion. Okay, priority inversion. Let's say I have two processes, process L and process H. Okay, why I have chosen these two letters for them will be clearer. Let's say process L has a critical region. Let's say this is start critical and end critical, and process H again start critical and end critical. They have both critical processes, and the reason why I am calling this L and H is this: H has a higher priority, L has a lower priority. That means the operating system will let H run, if it is runnable. Okay, L will never get a chance to run if H is runnable. Okay, L runs only if H is blocked. Let's look at this one. Okay, this is what I said. L never runs if H is runnable. Let's say while S is sleeping, okay, H is sleeping, let's say, the low priority process L grabs the spin lock. Okay, it says that L says that I like to get the lock, and it gets the lock. Okay, and it is inside this critical region somewhere there. Okay, it's running the critical region, and then H wakes up while this one is in the critical region. H wakes up, it tries to get the lock using this one or this one. It will say that I like to get the lock, and I am in a spin lock, in an infinite loop. H will run. If there is an interrupt happens, the operating system will check if anybody else is ready to run. L is ready to run, but I cannot let L run while H is runnable, and it will let H run again. H will run in an infinite loop, and L will never find a chance to run so that it can release the lock. Okay, H wakes up and tries to get the lock. It spins, waiting for L to free it, but L can't get the CPU, so it doesn't progress. So L will be interrupted in this critical region. L cannot, although it is ready to run, operating system will never let it run, okay, because H is runnable, but H is running something stupid. It is running this infinite loop. Okay, so this is called priority inversion. Why they call it priority inversion? It says that in this case the priority of L is higher, because without L running finishing its job, H cannot run, but the operating system thinks that H has a higher priority. Okay, this is just one example of a deadlock. And if we have time at this end of the semester, we will look at this. We will look at this deadlocks. Okay, priority inversion is an interesting problem, and it can happen with the spin locks. Okay, because H never sleeps. It says that I will run. I will run. Eventually, I will get the lock, but there is no way it is going to get the lock because lock is held by L. Okay, so what I said was spin locks are bad for efficiency. Also, they are bad for these kind of problems. Okay, so let's try to find a way to eliminate the spin locks. Okay, simplest way is sleep and wake up. We need system calls. Okay, instead of going to the top of the loop, you tell the operating system that I will go to sleep until this lock is ready, until I can get the lock. Okay, so in an example, I am going to introduce this problem, producer and consumer problem. It's a very classical operating system interprocess communication problem, producer-consumer problem. A very typical example is the Prince spooler. Remember the Prince spooler that we looked at? Let's go to there. Yeah, this one. Spooler is a consumer. This is a consumer. This one is a consumer. Consumer. And these two are producers. Okay, so these are consumer and these are producers. What we mean by producer and consumer, process A says that I like to print something, process B says that I like to print something, and this one serves them, it consumes them. So this is a typical producer-consumer example, and let's make this more general. We say that producer wants to add elements to bound the size buffer, and buffer is, if the buffer is full, the producer must sleep. Consumer wants to remove items from the buffer, and the buffer is empty, consumer must sleep. Okay, of course there is a buffer problem here, and also there is a race condition if you are not that careful. Okay, any questions? Is this priority handling yeah, operating system has to support the priorities, yes. Okay. Cosmos, I don't know what you mean Türkçe'ye geçecek miyiz? No, of course not. Let's look at this problem more carefully. We will produce something and we will put in a buffer, and if the buffer is full, I have to sleep. For the producer side, for the consumer side, if the buffer is empty, then I need to sleep. I don't go into an infinite loop. Emre, according to what operating system decide to process? Well, remember what we did last time. Okay, of course, this is my stupid Linux emulation. When I say AX, where is my AX P? I forgot how to get the priorities when I said the AF. Do you remember the option to get the priorities? Okay. Low priority, kernel switching priority. I think minus Y. What was the option? Minus Y? Y? No. AXY? P? I forgot. Remember when I say there is an option that tells you the priority of the process. The priorities are set by the operating system, or sometimes it is set by the user. Remember this nice? When I say nice ls, I am running this ls program at a lower priority. So the operating system has to support it. PS minus AL. No, PS minus AL doesn't tell you, does it? PS minus AL. Yeah. This is a priority. See, this is a priority. If I run another bash with a nice, and when I say PSAL, yeah, my bash, the second bash has a priority of 80. The first one, the second bash has a priority of 70. Since I am launching my PS with the second bash, is priority 72. So Windows is supporting these priorities. Operating system has to support it. Can we say that my program lower priority? Nice is a way of, yes, of course. Nice is a way of changing your priority. But nice is a one-way priority change. It only lowers your priority. Usually, operating systems doesn't let you make your priority higher. It's an administrative privilege. Okay, good. So let's look at this example. And let's say we have n number of elements in our buffer. Count is 0. This is my producer, that is the program trying to print something. This is the consumer, this is the spooler. While true in an infinite loop. Okay. I produce an item, whatever it is, just a regular thing. It produces an item. If count is n, that means that my buffer is full. I need to go to sleep. I need to wait. If count is not n, that means I have slots available. I insert my item. And then at the end, if the count is 0, that means that the buffer was all empty. Okay, before I insert anything, I wake up my consumer. But what do I mean by that? If the buffer was empty before I inserted anything, that means that no consumers are active, right? They are all sleeping. So I am waking the consumer. The consumer just does the opposite. If the count is 0, there is nothing to do. I need to sleep. Okay? If the count is not 0, then I remove the item. Okay? If the count is n, that means that the count was n. Since the count was n, then that means that the producer was asleep. Then I need to wake the producer. Then after that, I consume the item. So in fact, what's happening here, that one of them is in an infinite loop. It is producing something. One of them is just producing something. The other one is just consuming it. But it is not as simple as running two infinite loops. You need to put them in a special buffer, and you need to take care of how the buffer is full or not full. Okay. Oh, I have a question. Yasir, Yasir, are spin locks common practice in any modern systems, or they are obsolete? No, they are definitely used a lot. They are definitely used a lot. Why? Because you don't want to make a. What is the alternative for the spin lock? You need to tell the operating system that you need to sleep, right? That's a system call. System calls are expensive. But if you know that if I take a few loops in a spin lock, let's say 5, 10, 100, that would be much faster than making a system call. Okay? That would be much faster than a system call. So if I do maybe 100 times a spin lock, after 100 times I would say that that's enough, I am sleeping. That would be a much better solution. So the pure spin locks are not that used much. Okay? But a hybrid solution that uses spin locks plus the sleep, wake up system calls are used a lot. Mustafa, it is ring buffer. It could be, yeah, but it doesn't matter if it's a ring buffer or a open-ended buffer. Doesn't matter. All you have is just n number of slots available. The slots, number of available slots are not infinite. Okay, so I need to be careful. So this is a typical producer-consumer code, but as the title says, there is a race condition. Okay, there is a race condition. What is a race condition? Race condition is this. Let's say I am checking this one. I am running this one. If count is 0, I saw that the count is 0. Then I am going to sleep. Okay? Then I am going to sleep. If count to 0, then I am going to sleep. That's what I am going to do. I get an interrupt here, just at this position. Before I go to sleep, I get an interrupt. Okay? And my producer started running. It produced an item. Count is not n, count is 0. It inserted the item. Okay, it inserted the item and it said that the count is 0. I will increment the count and I will wake the consumer. Okay, it said that I am incrementing the count and I am waking the consumer. It sent a wake up call to the operating system, and operating system took this call and said that nobody is sleeping, so I will ignore this one. When the context switch happened again, when I come to this one says that I'm going to sleep, and operating system says that, okay, you go to sleep. So this one starts sleeping, and this one thinks that it sends a wake up signal to the other process. So at the end, this one started sleeping, and this one is never going to wake it up. Okay, so there is a race condition. So if the interrupt happens here, there is a problem. The same problem here too. If interrupt happens right at this position, okay, two problems. Right this position, interrupt. If the count is n, I'm going to sleep, but before it goes to sleep, let's say context switch happened, and it says that, okay, count is n, I will decrement it and I will wake the producer, but operating system says that nobody's sleeping, so it is ignored, but this one goes to sleep after the context switch. So we need to do something about this. Of course, what we can do is, before checking the count and going to sleep, maybe I can say use a TSL instruction. Maybe use just something like this. Okay, enter region, leave region. We could do that critical region thing, right? We say that, okay, let's put this. Let's say that, okay, this is my beginning of the critical region and end of the critical region, beginning of the critical region and end of the critical region. If I do that, then I can prevent that kind of no. Beginning of the critical region is here because I'm checking it there, right? Okay, so maybe I can prevent it, but there are better ways of achieving this, standard ways of achieving this, and we are going to see this. Okay, and we need to handle the buffer size, also the mutual exclusion, etc. with this solution. Okay, good. Let's move on then. The solution, okay, as I said before, I can solve this problem using the using this solution, TSL solution, or the exchange solution, no problem. But I like to use standard ways of solutions for this. That's one thing. The second thing is that, remember, our TSL and exchange solutions, they are spin locks. I am trying to prevent spin locks in this solution, right? I don't want to use those kind of spin locks. Okay, so let's see what people have found. Okay, we are going to use semaphores. The name semaphore looks like it is something sophisticated, but semaphore is a simple integer, right? When I say I have a semaphore, let's say S1, S1 is just an integer, okay? And since they are integers, there are operations that you can do on them. There are only two things that you can do with the integers, okay? In this case, either up or down. Let's say at the beginning it is 0. When you say up, it just increments the value by 1. When you say down, it just decrements it by 1. But I don't increment or decrement these using the regular operators. I ask the operating system to decrement and increment it. Okay, so you need to make a system call, or you need to ask your threads library to make this incrementation and decrement. What does down do? Down does this. Decrements the semaphore variable if it is greater than 0. If it is 0, it is doing something else. But if it is greater than 0, let's say its value is 5, it just decrements it. That's it. If the value is 0, it just goes to sleep before doing the decrement. Okay, since it is 0, it's not going to decrement it. It says that, okay, since it says 0, I will go to sleep before I decrement it. That means that somebody is going to wake me up. When I am waken up, I will decrement it later, and in that case, my semaphore will be greater than 1. Okay, so all this check, decrement, and sleep are atomic. It is done, supported by the operating system. So down is regular down, regular decrement. If it is not 0, it is regular, no problem. If it is 0, it says that I am going to sleep before the decrement. When I wake up, I will do the decrement later. Okay, but this decrement will never make this S1 a negative number. Okay, up is something similar. Increment the semaphore. Okay, it just increments the semaphore. If a process was sleeping on it, wake it and let it do its decrement. It says that I am incrementing this one. Let's say S1. I am incrementing it. If anybody is waiting on it, if anybody is sleeping on it, I will wake them up. Okay, so this idea of semaphores are very nice. They generalize well to multiple users. Okay, multiple processors, etc. And 1965, it is used a lot by the operating systems, thread libraries, process libraries, etc. Okay, and we are gonna implement this producer consumer problem using this semaphores. Since I have the semaphores, I will use down and up to count the number of slots available in my buffer. Okay, that's what I'm gonna do. Also, I need to use a binary semaphore, that is a semaphore that can become only 0 or 1 to achieve my critical region. Okay, any questions about the semaphores? They are not complicated. They are simple integers, you can think, and they are managed by the operating system or your threads library. Okay, they are used for incrementing and decrementing some values. The thing is that for the decrementation, if the value is 0, it doesn't decrement it. It goes to sleep before the decrement. It's going to decrement it anyway, but when it decrements it, it's going to be greater than 0. Okay, to make it greater than 0, it goes to sleep before that. Okay, and wake up, up is something similar. It says that I'm going to increment it. Okay, after I increment it, if somebody is waiting on it, then I will call that one. I will wake up that one. Okay, so we could use the semaphore as a tool to implement the critical regions. Let's say my semaphore is it's an integer. Let's say this is an integer. Just decrement this integer. Since it's a 1, it just decrements it. I entered my critical region, and after I am done with the critical region, I just increment it. If it is 0, let's say if it is 0, when I say decrement this value, I cannot decrement it. I need to go to sleep. Why? Because it is 0. And I will not wake up until that mutual exclusive semaphore becomes greater than 0. When it is greater than 0, I will wake up. Operating system will wake me up, and I will decrement it. I will enter my critical region. So as long as I have my mutual exclusive variable as 1, I can enter this critical region. But once I am in the critical region, nobody can enter it because I decremented it. Yasir says that our up and down are system calls. Depending on your implementation, I mean, pthreads library, if your threads are implemented in the kernel space, then you can say that these are system calls. But most of the time, they are implemented by the libraries, and you handle these kind of things without going to the operating system. But it's an operating system thing, and it's a library dependent thing. Okay, good. So this is just one way of achieving critical region. What is the advantage of this over the TSL exchange instructions, implementation of the spin locks? Of course, these are much more efficient. Why? Because when I enter the critical region, if it is available, then available. Otherwise, I have to wait. I have to wait in a sense that not busy wait, but efficient wait. Doğancan has a question. If Dijkstra invented semaphores in 1965, what is the point of Patterson's solution made in 1980? That's a very good question. So what is your guess? What's your guess? We have a very good solution with the Dijkstra. Yeah. So Doğancan, that's a very good question. So why do we need to have Patterson's solution 15 years after much more efficient solutions of semaphores are invented? That would be a good midterm question, actually. Let me copy it. I will copy this one. I will copy this one and put it to my email it to me. No, maybe how am I gonna? Okay, just email it to me. Yeah, I will email it. Somebody's typing. I need the answer for this one. That's a very good question. Okay. Last question. Yeah. Okay. So the answer is ontogeny. Well, Yusuf, that's a very good answer too. But that will not get you very good points in the midterm exam. Yeah, that's the actually answer. No, the first one is much better. Ontogeny recapitulates phylogeny. Yeah. The thing is that, remember, what do we need for the up and down? We need operating system help, right? How does the operating system achieve checking, decrementation, and sleeping in the atomic way? It needs help from the CPU. If the CPU doesn't support it, let's say in 1981, you have the Intel 404 processor, right? that processor, I bet, doesn't support any exchange instructions, right? Exchange instructions or TSL instructions. So you need to find a solution that can be implemented using regular instructions. Then in that case, I need to go back to the beginning of the computer science and use whatever available in there, right? So use Peterson's solution. Peterson says that, of course, busy waiting is not good, but if the CPU doesn't support any atomic instructions for TSL, and my operating system doesn't support up and down, what am I going to do? I have this nice compact solution, and you can use this solution on your PCs. Okay, so both of the question and the answer was good, but again, Yusuf, if you say the answer is antigen recapitulates phylogeny, that will not give you very good. That will not get you very good grades. You need to explain it a little bit. I bet you had the idea, but okay, good. So that means that this online teaching thing may work. I don't know, but I hope the other people's are. I still have 77 people. Okay. Good. I don't know who these 77 people are, but maybe some people from Gebze Yeni Mahalle. That's okay. My sister is watching my videos too. Abla, are you there? Abla? Maybe she doesn't. She just comes in and puts a like and goes away. Okay. So let's say implementing so I need to implement up, down, and up. Okay, this is typical done in the kernel. A question and answer to you. Who asked this question? Yasir, this is your question. Typical done in the kernel, but you don't have to. While I am implementing this, you must interrupt or disable the memory bus on the multiprocessor test and set lock protection as well. Okay. It only takes only a few microseconds. So we have a visitor.
Oh,
They don't see you.
they didn't see me.
Yeah, because you need to go there.
Where?
Just it's a delayed. Just stay there. Just a few seconds.
It's over a minute.
I have a delay of 30 seconds maybe.
30 seconds. Oh.
More than 30 seconds. But you know, the operating systems are like 60-year-old stuff. So we are not in a hurry. And this Corona thing is going to stay for a while. So this is what we do. Okay, so the implementing of the semaphores is usually done using test and set lock protection. And it gets lots of help from the hardware, and the CPU knows about it, and the operating system knows about it. For the Peterson solution, it's a software-only solution. It's a very nice solution, but it uses the spin locks. Okay, good. So this is the solution for the producer-consumer using the semaphores. Okay, I need 3 semaphores. One is a mutual exclusion for the critical region, entering the critical region and leaving it. The other one is a counting semaphore. It will count the number of empty slots. At the beginning, I have n slots, and I have another semaphore that counts the number of filled slots. Okay. So I have total of 100 places available at the beginning. N is 100. Infinite loop and infinite loop. Okay. So produce item and consume item is here. We are doing all of this stuff just for these two. Produce and consume, produce and consume. Of course, whatever I produce, I need to insert. Whatever I consume, I need to remove it from the buffer. Okay. So this is my critical region. Down, empty, and no. Critical region like this one and this one. It's a mutex. I down it if it is 1, I make it 0, and I enter the critical region. I insert my item and exit. I up it. This one says that down. If it is 0, then it's going to sleep, right? So I will sleep either here or there. That's one possibility to sleep. The other one is this. It says that as a producer, I need to decrement the number of empty slots first. So decrement is empty, which is 100 at the beginning. Since it is not 0, I will down it. I will decrement it. I will down my mutex. I will insert my item. I will up my mutex. But see, I don't up my empty. I up my full. Full says that, okay, full says that at the beginning the number of filled buffers is just 0. So I incremented full. Why am I doing this? Because this guy is down, it's decrementing full. It says that I will decrement full, which is 0 at the beginning. So at the beginning, consumer will be blocked. It will go to sleep. Okay? It will sleep until somebody produce something and incremented this one. Okay? This one will not enter into this region before somebody makes this full, at least one. Okay? And after that, it will say that I need the critical region mutex. Then I will remove the item. Okay? Up mutex. Then it says that I will up empty. I will up empty. If empty was 0 before, that means that somebody is waiting on it. Okay? So it ups empty. Okay? Good. So this is the whole solution. So somebody's asking me, yes, kinda. Is that my sister? S2MLE 100 Lesh? No. Somebody's making fun of me. I think I will kick this out. I will kick this person out. If this one is my sister, then well, I don't want to be disrespectful. I will call my sister. Take care of this one. Maybe I will call my sister after that. No, I am out of time anyway. S2MLE 100. I don't know what this is. Okay, I will kick this person out anyway. Add hide user on this channel. No, okay, no, I will not. That's okay. He or she didn't say anything bad. So this is the whole consumer producer thing, and let's see if the places where we can sleep. Where are the places that we can sleep? This one is sleeping. Yeah, that sleep can happen only with the downs, right? Sleep can happen only with the downs. This one sleeps. Okay, and this one. There are 4 places. There are 4 places where you can sleep with this example. When this one is sleeping, that means that there are no empty slots available. It is all filled up. When this one sleeps, it says that the consumer full. It says that there are no items inserted inside the buffer. I need to wait. Okay. If this one is sleeping there, okay, this one is sleeping here, then I need to make an up call with the empty. Okay. And if I am sleeping here, then this one will wake it up. Okay. So why do I need empty and full? I need them to take care of the buffer. If I have empty space and full space and etc. I am using semaphores to get help from the operating system. Okay. So empty and full are for that. Mutex is for entering the critical region. entering the critical region. Question. If I remove this one, no, let me make it, okay, remove this one, this one, and this one. Would it work? Would I have race condition in this example? I don't understand what up and down function does. Oh, okay, let's go back to then. I mean, Ali Emre, the definition of up and down are here, right? Up just increments this one, down just decrements it. But there are exceptions. When this one is 0, down doesn't work. It just doesn't decrement it. It just goes to sleep. Okay? Who wakes it up? Somebody that increments this S1 wakes it up. And up says that I am going to increment this value. If somebody is waiting on it, then I will wake them up. Okay? Up never sleeps. Down sleeps. Okay? Down never wakes up somebody else. Up wakes up somebody else. Okay? Ali Emre, is that okay? It's not, I mean, if you look at this example, this should be clear enough. This will go to sleep if MEX, mutual exclusion, is 0. Okay, this will go to sleep. It will not enter this critical region unless somebody makes this MEX variable non-zero value. Who's going to make it? Using a, okay, good. So let's any answers to my question? If I remove these mutexes, if I remove these 4 lines, what happens? Do I need them? Because I already have 2 semaphores and they are good for synchronization race conditions. Why do I need these mutexes? Is there any way I can save all these questions and everything in the YouTube video? I don't know. Any answers? Why do I need mutexes? When you answer that question, I will ask the other question. Why do I need empty? Why do I need 2 semaphores to count the number of empty slots and full slots? Okay, maybe I should stop here and I will start tomorrow's lecture with the answer from you why we need those mutexes. Okay? So that's it for today. If you have any questions, I will stay here for a while and I will try to answer them. Again, you may call me from my phone. Yasir is giving me an answer. Aren't the empty and full used to keep the size of the buffer and mutexes for the critical region? Yeah, that's true, but I need to down empty and full anyway. They will be blocked anyway, so why do I need the mutex? It can be read white buffer. I don't understand what you mean, Emre. Yeah, Yasir is on the right track. I mean, keeping the size of the buffer is something that we need to do, yeah. Yeah, Antonio, the stream will be saved to YouTube, but So you mean that let's let the people watch the stream video, not the uploaded video? I am not sure about the quality of the saved stream because unfortunately our internet connection at school is not that good. I get breaks from time to time. So people need to go to the stream then, maybe. I hope. Okay, we will do it that way. Oh, maybe I can do this. Okay, maybe I can do this. Just open the YouTube and go to live. And in that place, I have the comments in there. And if I do this, well, it doesn't look like I have many questions. Oh no, it doesn't keep all the questions, all the chat. Maybe go to my channel. Anyway, I think the stream save will be good enough. Okay. So I'm looking at the question now. In this example, mutex can be 1 or 0 while full and yeah. Okay, so Yasin, those are good answers. We will continue with this tomorrow then. Okay, I'll see you tomorrow. And I will be here for a while, as I said. Let me go get some tea. And if there are any questions, I will answer them after that. I will stop the stream. Okay, thank you. I guess no questions. Okay, thank you then. See you tomorrow.